Well, hello BC Calculus students. Looks like we are ready for today, which we are going to be today looking at trig substitution again, and specifically we are going to look at, that doesn't look very clear. Let's see if I can make it be a little more clear. Maybe that's okay. So we are going to look at trig substitution, and we're going to look at special formulas. And a lot of what the truth is, all you got to do is know the special formulas, but a lot of it, this will give you some practice with, or at least give you an example of how to use trig substitution, get you a little more familiar with it, and motivate you to learn the special formulas. So let's look at the following situation. Let's consider the integral of the square root of x squared minus 4 dx. So this presents itself right away. This is a trig substitution situation. You can't use u substitution, so we're going to do trig. So let's build our right triangle. Building our right triangle, we have this right here. The truth is, the first time I built this, I put the 2 over here, and I put this right there, but then I figured out as I started to do it that that would mean that I was working with all cofunctions. Cosecants, cotangents, and since I'd rather work with tangents and cotangents, it's easier to put this where the variable is there and the constant is the adjacent side. So, but you can do it either way. You can do it all with the cofunctions if you want to. So doing this, what I can know is I can know that the tangent of theta is going to be that square root of x squared minus 4 over 2. Which means that if I solve that for the square root of x squared minus 4, I get that to be 2 tangent of theta. And if I want to express x, notice over here looking at x, I can see x would be 2 secant theta. So just like the secant of theta would be x over 2, then I can multiply by 2 and I see x is 2 secant of theta. So with that, I can go ahead and find my dx. Which if I find my dx, taking the derivative of, put a separation in there, taking the derivative of 2 secant theta, I get 2 secant theta tangent theta d theta. So now I can go ahead and I can substitute in. So what I'm really trying to find the integral of is this, which is 2 tangent theta times 2 secant theta tangent theta d theta, which if I go ahead to do that and bring out those constants, I get 4 times the integral of the tangent squared theta, secant theta, d theta. All right, so how am I going to integrate this? Well, you can look and manipulate and see. It'd be nice if there was a u substitution because I see a secant and a tangent together, and I was thinking, well, if I could integrate that, but there's not tangent. If I let u be tangent, I get a secant squared, but I don't have a secant squared there. So I'm really kind of stuck here. If I let u be secant, then I have secant tangent. I don't have another secant to go there. So it looks like I'm going to have to do some manipulation here. So what I'm going to do is the type of thing that we did back when we were doing some u substitution situations where we had to do some. Now this is doing some trig substitutions. This is the actual trig substitution right here. But what I'm going to use, I'm going to use some trig identities to do some re-expressions, basically, a good way to put it. Do some trig re-expressions here. So what I'm going to recognize here is this is probably going to be, situation has to be done. A lot of times we can think of, well, if it doesn't work to do it u substitution, then let's try integration by parts. So if I do integration by parts, the key thing here is, remember, I'm going to get an integral of v du. So what I want to do is I want to pick something for dv that when I integrate it, it doesn't get worse. If anything, it gets better. And I want to pick something for u that when I take the derivative of it, it also gets reasonably better. So notice, in order for me to, what I could integrate here definitely is I see that I've got a secant tangent, a secant and a tangent, and that could be integrated. So I'm going to let that be dv, the secant tangent, which lets just tangent be my, my u. So my u is going to be tangent of theta, which means that my du then is secant squared theta d theta. My dv, like I said, was going to be that secant theta tangent theta, because I know I can integrate that. And if I integrate that, I get the secant of theta. So using this, I can now go ahead and I can re-express using my integration by parts. So I have 4 times the integral of tangent squared secant theta would be equal to 4 times, and now I go uv, so my u times v is going to be secant theta times tangent theta minus the integral of v du, which is going to be secant theta times secant squared theta, so that gets me secant cubed theta d theta. Okay, well, let's see what happens here. So I'm going to go ahead, the next step, I'm going to say this is equal to 4 secant theta tangent theta. Now this, I don't have a way to integrate that, but let's see if I can break it up. I could break it up into secant squared times secant. So breaking it up into secant squared times secant, now I can replace secant squared with 1 plus tangent squared using my Pythagorean identities. So I'm just breaking that down. Now notice I can distribute this secant in here, and I get this. But notice what I've got here. I've got this, which is exactly the same as this. And I know this is equal to this expression here. So I can add this 4 times the integral of tangent squared secant d theta to both sides. It'll cancel out this integral here, and I'll just put it over there. So this gives me 8 on the left side of those tangent squared theta secant theta d theta. And that's equal to 4 secant theta tangent theta minus 4 times the integral of secant theta d theta. Now remember, what I'm trying to find is I want to solve for 4 times this, so I don't want 8 of those, so I'll divide by 2 to get 4. I'll divide both sides by 2, and I get to this expression right here. So dividing both sides by 2, I get this. So all I have to do to find the answer to this is just integrate the secant of theta d theta. Not too bad. Well, maybe. You've done this before. This is one that a lot of times people will remember, and you'll see why pretty quickly here. I'll assume you don't remember it, and I'll go ahead and do it. So this is equal to, just rewriting this, minus 2 times the integral. And that secant theta, I'm going to have to multiply that by secant theta plus tangent theta over secant theta plus tangent theta. Notice that's just multiplying by 1, so I'm okay. Distributing this through in the numerator, I get the following. I get secant squared theta plus secant theta tangent theta in my numerator, and my denominator is just secant theta plus tangent theta. Of course, the advantage here is now I can use u substitution. I can let u be secant theta plus tangent theta, the denominator, makes du my numerator. So this just becomes du over u, which I know when I integrate that, it's just the natural log of the absolute value of u. So this is going to be 2 secant theta tangent theta minus 2 times the natural log of the absolute value. And remember what u was. U was the denominator. So I get secant theta plus tangent theta plus a constant. Okay, so looking pretty good, except that I've got no more integration to do. I've solved this bear of an integration problem, but I'm all in terms of theta instead of x. So I've got to go back to my triangle and see if I can re-express the secant of theta and the tangent of theta in terms of x. So scrolling this back down so you can see the triangle, notice what I'm going to have here is the secant of theta is going to be x over 2, because that's the reciprocal of cosine. And the tangent of theta is going to be the square root of x squared minus 4 over 2. So going back in here and replacing those, I've got 2 times, and notice my secant of theta is going to be x over 2, and this is going to be the square root of x squared minus 4 over 2. So this is going to have a denominator of 2, this is going to have a denominator of 2. So when I multiply them together, I'll get 4 divided by 2 divided by 4 becomes 1/2. And then notice my numerators were x and the square root of x squared minus 4 right here. And then minus, and I have 2 times the natural log, and in for secant, remember, is going to go x over 2, plus, and in for tangent goes the square root of x squared minus 4 all over 2 plus c. So I have now got my answer. About this time, what I'm hoping by showing you all this is you are now sufficiently motivated to say, I don't ever want to do this. This is a rather long, drawn-out process. Now, it does get easier if you have memorized what the integral of the secant of theta is, and you can just look at a table and get that. That would certainly help you out. Sometimes people have a table where they have written down what the integral of secant cubed is, because notice at one point here we had this integral of secant cubed, and so if you had that already, from a table or memorized, you could have just simply said it was going to be 4 times the secant theta tangent theta minus, and then you could simply write in that integral there. But assuming you don't have those, this is the process you have to go through. Because this is so messy, and because this is a pretty standard form of a situation, remember right up here, right up there, we are going to have formulas for these basic types of situations. I would suggest that these are a good thing to know. The truth is, I know everyone's going to ask, no, I'm not going to test you on it. But this is the type of thing where you should know to have access to them and know where to be able to get them. And you'll be able to use them on the homework today, so it'll make certain problems easy because you'll just have to plug in. But let's look at what the special formulas are. First, if you have to take an integral of a squared minus, or I should say the square root of a squared minus u squared du. Notice here's the constant minus the function that is squared. We know the answer to that is going to be of the form 1/2 all times a squared times the inverse sine of u over a plus u times the square root of a squared minus u squared plus a constant. So if you get this, rather than having to go through this long, involved, drawn-out process, you can simply use this formula and go ahead and take whatever a is and plug a in accordingly, and whatever u is and plug in u accordingly, and you have your answer. Our second special formula, this is the form we had. Our u here was our x, so this is where we had our x squared minus our 4. So notice the formula here yields 1/2 times u times the square root of u squared minus a squared minus a squared times the natural log of, and then we have the absolute value of u plus the square root of u squared minus a squared plus a constant. Now, if you notice, this is a little bit different looking than what we got here. But if you check, you'll see that, remember, this is a generic form, and we solved a specific problem. So does that mean we got the wrong answer? No, it doesn't mean we got the wrong answer. If we look at what the generic form would give us, we would see that that really is a form of what we got. So notice we would have this 1/2 here. If I distribute this 1/2 into this, in this case here, I just get this 1/2 times that. If I distribute the 1/2 into this, I would get 1/2 times a squared. But notice my a squared was 4, so I would have 1/2 times 4. That would give me my 2 right there. And then over here, I have my 2 in my as my denominator, and that one actually just becomes part of the constant because it can be taken care of as part of the constant, because if you want to think of it this way, this could be thought of as I could add these two up and make it the natural log of x plus the square root of x squared minus 4 all over 2. But then that would be the natural log of a fraction, which means it would be the natural log of the numerator minus the natural log of the denominator. But the natural log of the denominator would just be 2. Well, that would be a constant. And so then that constant would just factor in with that constant. And so it really is the same answer. It's just a different form of it, where we have that constant inside the natural logarithm that we could get rid of it, but it's just not gotten rid of in this case. So these really are the same answer. If I put the 2 in for A into this one here, it would actually be an equivalent expression to this. It's just a different form. The difference is that the C would be different in this one and in this form here. The C's would be different. Okay, the final form is if we have a sum underneath the radical. So we have the integral of the square root of u squared plus a squared. The good news to this one is it's exactly the same as the formula for the previous situation, except the only difference, instead of a minus in between these two terms here, we have a plus. Other than that, it's exactly the same. Well, and of course, what's under the radical matches what's under this radical here. So if you want to think of it that way, these signs are all negative on this one. These signs are all positive on that, except for this one in here. When we're adding those two, that's adding in both cases. So I guess we do have to be a little bit careful. It's not quite like it's all pluses and all minuses, because in this one here, that is a plus right there. Okay, hope you're sufficiently motivated to use and know your special formulas. Your exercises are 17 through 27 all. Some of those are going to be use special formulas. I think 4 of them are those, or maybe more. Some of them can actually be done without using trig substitution. You can do it just with u substitution. When you can, do it. It's quicker. But when you have to use trig sub, use it. Okay. That'll be that. And if you have questions on this, we will be having a Zoom session tomorrow. Hope it's going well. Talk to you later.